Yes, Densei, the floor is yours. Welcome.
Shall we start?
Yes.
Hello. Okay. Hello, everyone. Welcome to attend this panel on evolution of 5G mmWave. I'm Zhenfei Tan. I will moderate today's discussions. Today we have 5 distinguished panelists. I give brief introductions. The first one is Edward G. Tiedemann. He's just leaving, not in the screen. Hello, Tiedemann from Qualcomm. Hey. Okay, next one is Mr. Rui Sun from Huawei. Hello.
Hi. Hello, everyone.
Yeah, the next one is Dr. Stephan Parkwald from Ericsson.
Hello.
Hello. And we also have another 2 panelists. The next one is Dr. Fuchan Li from China Unicom. Unfortunately, he has some unexpected agencies. He cannot join our live discussions. The last one is Professor Wolfgang Wood. He will join us a few minutes later. So, so let's start our sessions. Firstly, let's play our pre-recorded videos.
Hello, everyone. Welcome to attend this panel on evolution of 5G mmWave. I'm Zhenfei Tang from Huawei, today's moderator. We have 5 distinguished panelists on this panel, from operators, vendors, and university. I hope we can have a very interesting and great discussions in this panel. As we all know, 5G mmWave already deployed in some countries. 5G mmWave firstly have ultra wideband, which makes it very attractive. But at the same time, due to large propagation and penetration loss, one mmWave cell only cover limited areas. Beam-based mobility is also one of niche features for mmWave by using hybrid or analog beamforming. 5G release 16 standard was frozen last year. So in April this year, 5G Advanced as a new marker was agreed by 3GPP, which opened a new era of 5G evolution. In addition to enhanced capability for eMBB, MMTC, UNLC, more use cases will be introduced in 5G Advanced. So it is time for the industry to think about the evolution directions for 5G mmWave. For example, how the mmWave provides cost-efficient macro deployment, how to support seamless mobility, and which kind of new capabilities will be introduced for 5G mmWave. Today we have 5 distinguished panelists. I will take a few minutes to introduce them. I'm Zhenfei Tan from Huawei, the Senior Manager of 5G Evolution Research and Standard. I have been engaged in research and standard for wireless communication for the past 20 years. The first panelist is Dr. Edward G. Tiedemann. He is a EEE Fellow, a Qualcomm Fellow, a Senior Vice President of Engineering of Qualcomm. He leads Qualcomm's worldwide standardizations and industry organizations activity. The next panelist is Mr. Rui Sun, my colleague, a Senior Vice President of Huawei Wireless Research. He currently leading the 5G and beyond technology research and development. He joined Huawei in 2000. For the past 20 years, Mr. Sun has served as Director of 2G, 3G, 4G, and R&D. The next panelist is Dr. Stephan Parkwald. He is currently a senior expert and addtion research, working with research on 6G and future radio Earth. Is one of the key persons in development of HSPA, LTE, and NR. He has been deeply involved in CPV standardizations for many years. Dr. Parkwald is a fellow of IEEE and served as IEEE Distinguished Lecturer 2011 to 2012. And he is the author of several popular books. Many of us read his book. The next one is Dr. Fuchan Li, Deputy Director of Wireless Technology Research Department of China Unicom Research Institute. He is a senior engineer and professor level and a technology expert on patent examination in State Intellectual Property Office, enjoying special government allowance as well. The last one, not least one, is Professor Wolfgang Wood. He's a member of the steering committee of TUM Department for Electronic and Computer Engineering since 2011. Since 2017, he served as the dean of the department. For his contribution to signal processing algorithm, he has been evaluated to IEEE fellow. So I expect we can have interesting and great discussions today. I prepare some of the questions for discussion here. The first one is what are the top challenges in the current 5G mmWave deployment across the world? The second one is what are the top new use cases for 5G advanced mmWave towards 2025 and beyond? The last one, and also very interesting one, is I want to ask our panelists is what are top technologies for 5G advanced mmWave, considering the above use cases and also the challenges. At the same time, I strongly encourage our audience to raise your questions and also share your ideas on the evolution of mmWave. Your active participation is also very important for these panels. Thank you all. So let's first enjoy the presentation from distinguished panelists. Thank you.
I'm Ed Tiedemann. It's a pleasure to participate in this panel on millimeter wave. 30 years ago, I spoke at the first PIMRC held at King's College in London. It was a small conference with about 200 attendees. During that conference, I gave the first major public presentation on CDMA. What were the basics of what became the IS-95 2G standard and one of the major air interfaces in the history of cellular. That work really stimulated the industry to do the R&D that has led to our advanced cellular systems of today. This cover slide shows a photo taken on Mars by Ingenuity, the helicopter which is driven by one of our Snapdragon chips from several years ago. Before I was involved in CDMA, I had spent much of a career working on millimeter wave. Believe it or not, over 40 years ago, I was designing and building complex millimeter wave communication systems and designing modems for the military. In some ways, our goals were similar to that which drove the use of millimeter wave for 5G. Obtain more bandwidth to support higher data rates and capacity for communications. For these military communications, bandwidth also helped to build systems which are jam resistant and with low probability of detection of transmissions, so that the enemy could not launch a missile at them. The narrow beam width that comes from millimeter wave was also a tremendous benefit in reducing the error which a receiver could detect the transmissions. Thus, millimeter wave is not new. What is new is our ability to bring it to the consumer inexpensively and in the small form factor of a cellular handset. Before I delve more deeply into millimeter wave, I'd like to review the overall status of 5G. 5G enhanced mobile broadband deployments, particularly sub-6, that is the spectrum below 6 GHz, are going exceedingly well. There are over 150 operators of deployed systems. We're expecting between 450 and 500 million 5G smartphones to ship this year. and there are estimates of around 750 million to ship next year. That is more than half the total number of phones being shipped will be 5G. Millimeter wave is a somewhat different story. We have good support in many devices. However, deployment is considerably lower, particularly in many locales. Yet millimeter wave offers so many benefits for operators, starting with the available bandwidth. In the US, as in the case with many countries, over 3 times the amount of spectrum is available at millimeter wave compared to all the sub-6 spectrum in current use. With massive MIMO, it can provide huge capacities. This can be taken even further in the future by adding more antenna elements in both handsets and cells and enhancing the processing. The costs that mobile network operators pay to acquire spectrum is an important component of their overall business costs. Let's compare the recent auction at 3.7 gigahertz, comprising 280 megahertz of spectrum from 3.7 to 3.98 gigahertz in the US, with 2.4 gigahertz of millimeter wave spectrum in Australia. When you normalize the prices paid to cost per person to megahertz, you get that the US 3.7 gigahertz spectrum was about 120 times more expensive than the millimeter wave spectrum in Australia. Due to the difficulties in propagation from outdoors to indoors, and often between rooms and buildings due to high attenuation of wall materials, we know that getting the same coverage at millimeter wave as lower frequency requires many cell sites. But full coverage is not what we're after. Mixed scenarios where we offload capacity to millimeter wave in many locations, such as outdoor dense environments, inside event centers, in airports, train stations, and in many office environments will reduce the load on the sub-6 network, thus allowing sub-6 to deal with the more difficult scenarios, such as in building penetration. I'm going to get into that in a minute. This slide illustrates the peak rates that can be obtained with an actual Snapdragon device, using a combination of millimeter wave and lower bands. It also shows that millimeter wave provides the data rates when coverage is available. Sub-6 provides coverage, and we can transmit seamlessly between them. In my view, there was a misunderstanding by many on the usage of millimeter wave. OpenSignal, a company which analyzes mobile systems, is reporting that users are connected to millimeter wave less than 1% of the time. And from that, one could infer that millimeter wave is not providing much benefit. But this is missing how millimeter wave is actually being used. The phone is mostly being connected to sub-6 networks for control, as that provides better coverage. When more than a trivial amount of data is being transferred, that which actually puts a real load on the network, the millimeter wave is invoked. We are seeing high download rates on some networks. OpenSignal is reporting that they have measured an average download speed of 618 megabits per second on the Verizon network. In addition, we are seeing a significant reduction in delay for 5G, some coming from the reduction in TTI, but much coming from the operators paying attention to transport and other processing delays in their network. Now let's look in depth at several deployment scenarios. Verizon, a US operator, has announced the deployment of what they call 5G ultra-wideband in more than 60 arena and stadium. They are partnering with many sports teams, so if one points a Verizon handset at the player, then the handset almost instantaneously obtains live stats and real-time information about that player. There are also many views of the actual plays that are going on in the stadium, and the user can select whatever view they want to see on their phone. This slide shows Raymond James Stadium, a stadium of the National Football League, that is American football, that is used by the Tampa Bay Buccaneers, and was the site of the Super Bowl in 2021. Here we see measurements of the downlink data rates as compared to existing LTE in the AWS spectrum. As you can see, the average data rates are almost 20 times higher for 5G millimeter wave than for 4G. During the Super Bowl, more than 2.5 times more data flowed on 5G millimeter wave as compared to 4G on Verizon's network. Here I am showing a model deployment in San Francisco. We replaced every sector of the existing network in the center of the city with 5G millimeter wave. No additional cell sites were added, nor was there any attempt to optimize the network. We see that millimeter wave covers almost 65% of the outdoors. What is most important is even with what is called fair coverage, we are getting hundreds of megabits of data. With an optimized network and the addition of a few cell sites, as is being done with most deployments, it is easy to see how OpenSignal was reporting over 600 megabits per second. Subway systems are quite attractive for millimeter wave deployments. This scenario here looks at a subway station. Actually, it's in Beijing, where we replaced sites having both LTE and Wi-Fi APs, and they're replaced by 5B millimeter wave with dual 128 element antenna arrays. With the exception of a few problem areas, such as in elevators and behind stairways, we basically have full 5G coverage in this particular station. Let's look at an actual deployment in a Taiwan factory. Here we see excellent coverage and data rates, as shown by the sections in green, with obstructing machinery shown in gray, and autonomous roving vehicles shown in the blue areas. Millimeter wave provides immunity to interference, which is crucial to obtain the low delay, quality of service, and reliability that is required in many manufacturing plants. Millimeter wave is here. We are making it happen through the Snapdragon system on chip and integrated millimeter wave antenna assemblies with RF up and down converters, such as the QTM845, which is our 4th generation product. One of the keys for good millimeter wave performance in a handset is to have multiple of these RF antenna assemblies so that phone users' hands don't cover all the antennas. Many in the research community are turning to 6G. I'd like to point out that we are still in the relatively early days of 5G. There are still many deployments to come, particularly deployments in new use cases and further developments of the technology, particularly at millimeter wave. Many of the bands that are being developed for 5G and those discussed for potential 6G use, such as terahertz, are even higher in frequency than are currently being used for 5G millimeter wave. For us to be able to embark on successful 6G, or even to have successful deployments of 5G in new use cases, we must further 5G millimeter wave. Thank you very much.
Now, I will give you some ideas about the millimeter wave evolution for 5G advanced briefly. As we know, 5G networks have been deployed in many countries. More than 160 5G networks have been deployed all over the world. There are also more than 700 types of devices and 350 million users in 5G network. As growth of 5G networks, we found some new requirements from the networks and the 5G services. For example, uplink services will increase very fast as the video services deployment. Current uplink experience and capacity can't meet the uplink requirement. Second, XR application, including VR and AR, need not only broadband services, but also low latency at the same time. It will bring more challenges to current 5G networks. For 5G network, we can apply more new applications such as sensing, passive IoT, and positioning. And we should also enhance the capability of eMBB, URLC, and MMTC. So, Huawei and partners think we should bring more capabilities for 5G, that is 5G advanced, expanding from the 3 standard 5G scenarios defined by the ITU, eMBB, MMTC, and URLC. Huawei proposed 3 new additions: uplink centric broadband communication, UCBC, real-time broadband communication, RTBC, and harmonized communication and sensing, HCS, to form the 5.5G matrix. In these scenarios, Huawei predicts that 5.5G will vastly outperform 5G in many aspects. For example, continuing from 5G, 5.5G will cut down the cost per fit of eMBB by 10 times, deliver higher uplink capabilities by using UCBC to meet the requirement of 80% of 2B scenarios, provide Gbps downlink rates at a low latency of 5 milliseconds to increase the number of XR users, multiple users multiple times with RTBC, and enable full scenario high precision indoor positioning with low latency, with low power centimeter level positioning, and wide area high resolution sensing to enhance the safety of self-driving cars and elder care in specific areas. For millimeter wave solution, we should research new technology for 5G advanced also. I think we can focus on 3 aspects. For EMBB, millimeter waves coverage is not good enough for outdoor microsites. We should increasing the coverage performance and the user's experience to make millimeter wave network or outdoor continuous networks. Second, for uplink service. In some scenarios, millimeter wave can also provide better performance for uplink service. We should do more research in millimeter waves uplink performance. For 5G network, some new capabilities will be introduced to 5G network. Millimeter wave super narrow beam and broadband can be used to enhance sensing and positioning capabilities. As we know, one separate frequency band, only one microcell size can provide continuous coverage for O2O services and O2I services through window. It can be used widely in outdoor microsites costly. But the millimeter waves coverage is not good enough for this. So it is very important to research how to compensate the propagation and penetration loss, enabling microcell continuous coverage with 200 to 500 microcell ISD in downtown. I think we can research new waveform to change multiple CCs to single CC, so we can get a low PAPR and better coverage. We also know the narrow beam for millimeter wave make beam management very complex. We should design advanced beam management with super narrow base station and UE beam. For example, quick beam steering and tracking with low head and latency. To enhance coverage of millimeter wave, we can also add some new small node in network. Such small node must be very cheap to be deployed massively. And also research some new technologies to compensate off distortion. Coverage performance enhancement is the most important for millimeter wave, definitely. If we use millimeter wave in uplink service scenarios, we will also meet some challenges, such as huge bandwidth advantage, but low spectrum utilization due to millimeter wave HBF-based Tiedemann multiplexing. UE does not need the whole bandwidth in a specific beam. We can design novel RF architecture and optimal system capacity algorithm to enable flexible FDM, SDM multiplexing. Another challenge is that different TDD configuration for uplink heavy applications will introduce strong crosslink interference between different sites. We should design better crosslink interference suppression with large area and narrow beams. For sensing capability, we can use it in a lot of scenarios, such as in highway. We can use sensing in autonomous driving. We can make full use of super narrow beam and broadband features for millimeter wave to increase accuracy of HCS. Sensing capability and communication capability should be combined together in same hardware, same frequency, and the same air interface. At the same time, sensing can't affect the communication performance in network, and also sensing can help communication to get performance. At last, we hope we can continue our technical innovation to unleash all possibilities for 5G advanced. Thank you.
Hi, my name is Stephan Parkwald, and in this introductory talk, I will discuss a little bit about the 5G millimeter wave and the evolution thereof. At low bands, we typically use a sector antenna at the base station and an omni antenna at the UV. Simple and robust and well-known technology. Moving up to mid-band, typically an omni antenna at UV still, but we do beamform at the base station. When we go up to millimeter wave range, 28 and 39 gigahertz, for example, we do need beamforming at both ends, and I think that is well known to all of you. And one of the challenges here is to do beam tracking so that the base station and UV always find the best beam pair and agree on them so that we can communicate. From a standard perspective, we have the tools we need. So what we're seeing in the last couple of years is that the products are getting more and more mature with more and more advanced algorithms being implemented, both on the UV side and on the base station side. That is good news because we're seeing that the gap that we saw in some early cases between simulations and products is closing. So it's getting smaller and smaller compared to what we've seen in the past and better performance. Another aspect of millimeter wave is the need for a fairly dense deployment. And that densification may not necessarily come from millimeter wave as such, but may come from other factors like the capacity need, the need for high user throughput, especially in the uplink, and also EMF regulations that could limit the possibility to build out a certain site with more output power or more frequency bands. So there are other factors that could drive this densification, and that is good news because when the network gets more and more dense, it also means that millimeter wave gets more and more useful. And as we see here on the plot on the right-hand side, it is when we get down into sight distances of 200-300 meters or so that millimeter wave starts to shine. And if you compare the capacity in this bars here with the green line, which is the estimated capacity need in a few years' time, you can see for the next couple of years, you can actually do quite well with low and mid band when you start to densify the network. But in a few years' time, we need to move into millimeter range as well to meet the capacity needs. And when we already have that, at that point in time, already have that relatively dense deployment, hopefully, it's a sort of fairly easy thing to put up a millimeter wave site there as well and get a very high capacity. So if you have a dense deployment, it's very attractive to deploy millimeter wave already from day one here. And that is what we see sometimes, especially in the US, for example, which has deployed a lot of millimeter wave. So what can we do with 5G millimeter wave? Well, on existing grids, we can deliver very high data rates on hotspots. You can think about Super Bowl, for example. We can use it to offload lower frequency bands. We can use it to backhaul sites, of course, where we quite easily can have quite direct antennas. Fixed wireless is, of course, another application that's already been used. You can get gigabits per second in suburban environments and start to compete with fiber in some cases. Could also be some targeted deployments. We actually see that you can do outdoor to indoor coverage in some cases. Non-line of sight coverage is possible, especially going back to what I mentioned at the beginning, where we see that the gap between products and theoretical simulations start to shrink now when products mature. We are quite optimistic about the possibility to do outdoor to indoor and non-line of sight coverage to some extent in certain scenarios. So that is actually feasible. Of course, to do that, we needed good antenna gain, high output power, and so on. So that would help. But in general, one could say that millimeter wave expands the capabilities of the world's greatest innovation platform. And exactly what use cases we'll see in the future, that remains to be seen. But if AR and VR takes off, for example, that is one use case where we need a very, very high capacity and very high data rate. So that could be a suitable scenario where we need to deploy millimeter wave. So what can we do if we look a little bit into the future? Well, one of the things are already ongoing actually in release 17, where we extend the frequency range for NR from 52.6 up to 71 gigahertz. We still use the OFDM-based waveform we have in NR, which makes sense. It's still a good choice. Of course, we need to scale the subcarrier spacing, but that's an easy change. The main target for this extension is license-exempt 60 gigahertz bands, but also unlicensed bands that do exist in some places in the world in this range. But mainly it's low output power, relatively short range, which means that this frequency range could be quite interesting for factory automation. Maybe again AR, VR, where we need very high capacity demands in the indoor environment, for example. Looking further into the future, into the 60 era, one of the components for 60 that are being talked about is the sub-terahertz range, the 100 to 300 gigahertz range. It's of course not the only component in 60 and maybe not even the most important one, but it will be part of the overall 60 story. So looking at this sub-terahertz range, 100 to 300 gigahertz approximately, there is quite a bit of spectrum up there in some cases, so we can get very high data rates and also very high capacity. But it also comes with a number of challenges. For example, the propagation conditions could be even trickier than in the more traditional 20, 30, 40 gigahertz range. Components and implementation is more cumbersome. It's not as mature as in the traditional mmWave range. So components need to develop here, knowledge about how to integrate things, how to put together an antenna panel of these components. All this needs to mature and still is on the research table. But for certain scenarios and certain cases, it is an interesting frequency range that can be useful for some very demanding applications. With that, I stop my presentation and looking forward to the discussion. Thank you.
Dear industry partners and friends, good afternoon. I am Wolfgang from Earliest Technology Research Center, China Unicom Research Institute. Today, I will present about the mmWave technology evolution and business outlook. China Unicom achieved fruit results on the road of 5G construction and will provide more innovative 5G service in 5 years. As the business develops, the network spectrum extends to mmWave to fulfill the requirements of new business types. On one hand, China Unicom achieved fruitful results by 5G RAN sharing with China Telecom, building 470,000 base stations nationwide, which covers all cities and developed country towns, providing the high quality service through large bandwidth and high data rate. On the other hand, with the development of high capacity, high data rate, and low latency applications, the frequency spectrum will inevitably extend to the mmWave range. 5G mobile architecture will be based on a combination of low frequency band and mmWave. mmWave band has advantages of bandwidth up to 800 MHz and data rate up to 10 Gbps. China Unicom will continue to promote national economic and technological development in the field of communications and further develop mmWave technology and lead the 5G development. China Unicom continues to and networking solutions and continues to lead the development of the industry. In June 2019, we carried out the industry first mmWave 16-channel 4K HD video service display in MWC Shanghai. In July 2019, we assisted CAICT in establishing MTA and became a vice chair unit. In October 2019, we released the first mmWave technology white paper and clarified 3 major scenarios for mmWave deployment in 2019 Beijing PT Expo. In June 2020, we had an release of China Unicom mmWave development plan at MWC Shanghai. In October 2020, we released the winter Olympics mmWave plan in GSMA mmWave summit. In October 2020, we established high-frequency communication joint innovation lab in 2020 Beijing PT Expo. In February 2021, we had a mmWave display zone in GSM MWC Shanghai, and in this way, we took the world's first DSUUU mmWave demo. China Unicom works on promoting the maturity of the mmWave industry chain. mmWave is an important part of the 5G new infrastructure and a necessary means for operators to meet the industry requirements. China Unicom will close follow national policies and play the leading role of operators in the industry. China Unicom drives the development of the industry chain and making preparations for mmWave 26 GHz band equipment, chipsets, and terminals to serve the Winter Olympics. In Stage 1, we had mmWave supported in NSA mode with 100 MHz bandwidth per carrier DDDSU frame structure with release 15 features enabled. In Stage 2, mmWave has been supported in SA mode with 200 MHz bandwidth per carrier DDDSU and DSUUU frame structure, CADC features, and release 16 multi-point transmission feature enabled. In Stage 3, there will be more frame structures and release 16 features available. mmWave will also bring better experience for 2C, 2H, and 2B users. For 2C service, we are building a well-known brand through high-quality service to enhance the national image and brand value. Typical scenarios include transportation harbors, tourist attractions, and airports. 2H service cover apartments, houses, and business areas in which FWA networking method is suitable, where optical fiber is not easy to access or the cost is too high. We also provide 2B service to locations like smart factories, smart parks, and smart works, where 5G mmWave can be combined with MEC and AI technologies to provide customized solutions. 5G mmWave can also be used to provide service to audience, contestants, organize staffs, media, and partners in the upcoming Winter Olympics. As the scenarios illustrated in the slide. We are also working on cooperative innovation on key technologies in high-frequency communication. We established the first high-frequency joint innovation lab in 2020, carrying out joint technological innovation, promotion of standardization, research and development of new equipment, and pilot trials to promote the development of the industry chain towards next generation communication technology. That is all for my presentation. Thank you very much for your time and attention.
Hi everybody, joining this panel on the evolution of 5G mmWave comm. First of all, let me thank the organizers for inviting me to speak to you. My name is Wolfgang Wood, and I'm a professor at the Technical University of Munich. My main research activities are in multi-antenna communication algorithms, also known as MIMO communications. In this field, I have been contributing over the last 2 decades. Currently, I'm very much focusing on machine learning aided phi-layer algorithms. You might say, aren't these doing many? Yes, this observation is certainly true, but I at least can say that I started this research already in the 90s of the last century. Then at this time, I did my doctoral studies. I left then the field and came back to it again after a couple of years. I guess I'm supposed to say now something about 5G mmWave communications because that's the topic of this panel. What interests me as an academic researcher at most about this topic are the challenges, but also the chances that come with the radio propagation properties of the respective radio channels in mmWave comm. These properties are very special to the very specular nature of the radio channel in mmWave communications, which is somehow a curse and a blessing at the same time. Here I consider artificial intelligence and machine learning as an important technology to cope with these challenges in mmWave comm. In particular, in addition to reported and well-known opportunities coming with machine learning, I personally believe very much in machine learning as an excellent option and paradigm to provide prior information and to learn and capture prior information of the underlying radio propagation environment to all respective phi-layer functions. This is in particular true for mmWave comm with its particularly pronounced channel structures, as already mentioned. Here, machine learning, for instance, by means of a radio-compatible digital twin of the respective environment, that's a title of one of my recent research projects, might play a key role for guaranteeing enhanced performances. On the other hand, we all know that there seems to be skepticism about the use of AI and machine learning methods in wireless comm, which in my opinion deserves attention and requires a careful study of the applicability of the methods. But I'm sure there is lots of room to benefit from it. If you are also interested in this direction of the discussion, I'm looking forward to sharing my further thoughts on this topic with you and learning about your experiences and opinions as well. Thank you, and see you then for the open discussion.
Hello, Professor.
Hi, hello everybody.
Hello. So now let's open the discussion now. Thank you all the panelists for your great presentations. When I discussion, I also encourage our audience to raise your questions in the question areas. So my first question I want to discuss is use cases. So recently they have some public news. And there are only in South Korea there are only hundreds of mmWave base station deployment so far. Compared with his what he's planning, is far away from what he's planning. So so at this time, so we have to think about the main use cases for mmWave deployment. As our panelists already present that have many use cases. For example, the traditional eMBB deployment. Maybe another use case a lot of panelists mentioned is the industry. Maybe another additional use case like a sensor, as Mr. Rui mentioned. So what's your views on the mmWave use cases, which can enable the mmWave large-scale deployment in the future? So who maybe Tiedemann take the first? Sorry, who is speaking? Maybe you can mute him.
Okay, do people hear me now?
Yes.
Okay, good. Yeah, you asked about use cases. Actually, there's a wide variety of use cases. And since I think you called on me first to talk about them, we've been, as I said, there's sort of these venue-specific deployments that we've seen, such as the stadiums or things such as certain in-building things such as subway places and things like that that you could look at. There's then sort of the semi-wide area deployment, which is really sort of the outdoor type deployments, which really help in like cities and things like that. And as I was trying to include in my presentation, sort of really could offload, say, your lower frequency sub-6 networks from a lot of the actual bit load where you do have coverage. The inside the building one is a bit trickier, and it really depends a lot about the construction of the building inside. And so areas where clearly there's a big space, putting up a few mmWave, I'll call it access points, and that can give you very good coverage. What's a little more tricky, for example, is a traditional office building. But when you have like sort of an open area where you have people sort of with little separations between things tend to work pretty good. If you have what I would call a more modern office building structure with drop ceilings, there's very good propagation sort of above that drop ceiling, and often diffraction and all going down into the actual areas where people are. So as I said, it's a little bit more trickier, but if you have sort of like big heavy walls, then of course the propagation to those heavy walls is a bit difficult. But I think the other thing is there's a lot of interest in factories here where, there's to deploy it, 5G ACIA and some other groups have been looking into, plus a lot of companies have been looking into deployments and things like factory environments, in such a mmWave. And then I think Huawei brought up there the nicety of mmWave with the very high frequency, high bandwidth. You can get very good positioning resolution and things like that are very useful for certain use cases, amongst that. So there's quite a variety of these, and I think we can continue to come up with more ones. It's really just sort of people going out there and trying these various use cases and sort of showing, how it works and what we have to do on deployments.
On use cases, I think it's always very difficult to predict use cases. I usually say, no matter what to say, you're wrong. Because, we didn't do 4D in order to enable YouTube or Facebook or something like that. But once we've done 4D, people figured out that, yes, they can run YouTube on it, they can do Facebook or whatever. So there's a little bit of balance between putting out the data rates there and ensure that you have the capacity, and then people more creative than I will come up with ways of using it. So it's a little bit hand in hand. But I think some of the kind of use cases that are relevant are these that require very high data rates, low latency, high capacity. So XR and VR, for example. Factors, as Ed mentioned, because the propagation condition is relatively controlled and decent, easy to handle if you have the antennas in the ceiling and so on. So I think these are some of the examples where you can use it. And in general, of course, city centers and city squares and things like that, where you have a lot of people, and train stations and these type of places.
Okay, for the use case, I think definitely the eMBB service is also the most important use case service for mmWave, because as the traffic of 5G network is growing very rapidly, maybe 2 or 3 years later, we will have not enough capacity for sub-6 G network. So, but not only for this EMBB service is not only in indoor services. I think for outdoor scenario, it's also necessary for EMBB. We should help the operator to build a continuous outdoor coverage network, outdoor continuous coverage network for mmWave. Maybe not only outdoor services, mmWave can also provide the service to cover the shallow area for indoor services by the outdoor sites. And for 2B services, I agree with the panelists that maybe the industrial services is the most important use case, and maybe better than sub-60 in this scenario. It can provide the broadband services use case in indoor scenarios, especially for uplink. Besides uplink services, so we can also use the mmWave for industrial camera to transfer the live video, for positioning and sensing services, also for some low latency for product line. I think mmWave can play an important role in this use case. Yeah, thank you.
Thanks. Professor?
I do not really feel as an expert to say something about this. As already Stephan said, it's very hard to predict, especially from an academic point of view.
Yeah.
It's very difficult to. So I'm just looking forward to what he said, but I would like to pick up what Abdelatif Salah said in this chat. Yeah, I think that's interesting. He said, "How can we guarantee?" I just try to put this together. That, for example, if we have AR and virtual reality stuff and so on, how can we guarantee the bandwidth, because mmWave is well known for maybe being unreliable? I guess that's a really good question, and this is what interests me a lot. Yeah, I'm not so much interested in the product, and I'm not an expert, but I'm very much interested in what I said in my short introduction. What kind of challenges come with this spectrum, and for me, this what offers are, yeah, and I personally think that such a question like how to address this might be a kind of personalization of the user. So I think maybe I have to rethink to offer a file layer or a network that is offering to everybody the same functions. Maybe we have to personalize the function that take into account a special channel condition and a special demand of the user. And how to do this, I could imagine that, as I already said, I'm quite positive that machine learning could help here. Yeah, but we can go in more details when we later talk about maybe technology aspects. But for the use cases, I'm definitely not the expert.
Yeah, I want to jump back in here because both the question and your comments make me, we really need to think not so much as mmWave in isolation. This is a point I was trying to make. We need to think of it in conjunction with the rest of our spectrum resources. And then when we pull these together, so yes, we can get where we get mmWave coverage, let's put our load there on the mmWave, and then that frees up some of our lower frequency bands where we have the more difficult, where we have better propagation and where we get into places where we don't have that coverage to pick those users up. And I think, and it's still yet to be fully proven, but I think if we can use these, then we get the real benefits of mmWave on the offload, and then we can really focus on getting that coverage with the lower bands. This is, by the way, this is an area where it could be used a lot of practical work in the field on real networks, plus some really good modeling, technique tools and techniques and all of that, maybe from sort of the academic sector.
One thought that comes to mind there, I fully agree with what you said there, that we should use higher and lower bands together, and that it's one resource. But one aspect on the coverage, and that we try to improve it, we try to have it connected. In some cases, people are happy that the railways don't go that far. I mean, there are some industrial settings, industrial applications, where it's good that the information basically stays within the building, that it doesn't go far outside the actual building and so on. So it could be used to an advantage as well in some cases.
Yeah, particularly with certain private network scenarios, as Stephan was explaining. Yeah.
Okay. Thanks for the sharing. I think I want to come back to this professor's answers for this personalized informations. And also the in this afternoon, I think the Stephan and Tiedemann also have some give also sorry, they have some noise. Can we mute them? Okay, so as Ruixun presented, is the one of the use cases is a sensing. So sensing is one of the very hot topic in the in 6G. So I'm not sure the sensing is also possible for the 5G evolutions to use mmWave. Can you share your views on this aspect? Maybe Ruixun Mr. Ruixun can take first.
For sensing, because the mmWave spectrum is available now for 5G network, definitely the operator will build a network with mmWave for EMB services. If we can embed the sensing capability or positioning capability in this network, so we can enhance the capability for the operator network. Those operators can maybe make a new business in this network. I think why don't we use it in 5G? If the use case we can make this use case successful in 5G network, I think maybe in 6G it will be more successful with new technology. But the business it can emerge in 5G network. So we can do research based on the 5G technology network now. That is my opinion.
Yeah. Okay. Tiedemann, do you have any comments on this?
Yeah. No, we certainly know that at millimeter wave, the possibility exists of looking at I'll call it some of the channel characteristics, which we can potentially do with and use that to both for the high bandwidth, the channel characteristics and things like that. We can obtain information about the environment. To me, the real question really comes from a practicality, a business arrangement here. How do we actually use these techniques in a way that provides the value directly to the customer, and how do we make the business sort of all of this sort of work? This is always, of course, a challenge with things, and then we have to sort of look at, is this going to be a better technology than say sort of the millimeter wave radar systems and things like that we find out there also. So we got to look at these things. As I said, it's not that we can't do sensing with millimeter wave. That's not the issue. It's how does this all fit together, from a business perspective, and how does this all work?
Okay, thanks.
The aspect of whether sensing is 6G or 5G or something else, I think, sure, there's a lot of sensing discussions in the 6G context right now. And it's one of the new services that we're looking into. And if that turns out to be, if you can do something sensible, we have some ideas on what type of business you can build around it. I don't see a problem why not introducing some form of sensing also in the 5G evolution track. We've seen that type of things being done before, that you develop something, you maybe talk about the next G, but then you also see it in the evolution of the previous G. So there could very well be some sensing things coming in the millimeter wave evolution of 5G. But then, as Ed said, yes, you can do it technically, but it, at least to me, quite unclear exactly how to sell that service. I think there are some use cases for it. It's probably it's very interesting to look into, but it's not yet clear how you can use it. Maybe it can be in some factory hall if you have some kind of intrusion detection or detect if you get too close to some dangerous machine or something like that. That could be one use case, but there are probably other things you can think about as well.
Mm-hmm.
Because it would be nice if if we could use, if we anyway deploy a network for communication purposes, if we can reuse that hardware, that deployment also for sensing, and get sensing more or less for free, so to say, that would be quite attractive.
I would pick up the latter. I think this is really a very interesting question. How can we exploit the existing network, which is built for communication for sensing purposes? That would be, or somehow to rebuild it, that would be very interesting. The overall question, if we can use it for sensing, I think is already answered, because isn't automotive radar a mmWave technology? This is already what we do. Yeah. The question is, I think what Ed said is very, very true, and I can't answer that as good as you did. Yeah. Is it really a business? Yeah, and does it really make sense? I think this is what you can answer much better than I can do. But I think from an algorithmic point of view, this is what interests me most. Yeah, you can definitely do it, and we're talking about it in 6G, as Stephan said. Yeah, so but I don't know if it pays off, and if it makes sense. I don't know. I see a lot of. It's a very hard topic, but sometimes I'm a little bit missing what it really goes to, yeah, and what we are selling at the end. But that is what you know much better.
Yeah. I think for business is a problem for the operator for sensing capabilities. So if we make full use of the super narrow beam and the broadband features for mmWave to increase the accuracy for sensing. So the sensing capabilities and communication capabilities can combine together in the same hardware, the same frequency, and the same error interface. So the operator can have the capabilities or sensing capabilities in the current 5G mmWave network with no extra cost. So the operator will have the driving force to have the capability, because it's very, very cheap to deploy a sensing capability in his network. So he can provide some of the new services based on this, based on the sensing capability. So maybe this capability, this business may be emerging in 5G network. It will be develop a lot in 6G network. I think we can do it to help the operator as fast as possible, as soon as possible.
Thanks. Maybe we'll go to the next questions from my side. We'll discuss the EMBB deployment, and also Tiedemann also added this. We need to consider the mmWave together with other frequency band, for example, sub 6Gs. Then my question is, that's always the case, or if we want to enable mmWave massive deployment, can the mmWave can stand alone with wider coverage, continuous coverage? If the mmWave needed to provide very large coverages, then what's the most important sense? What is the most challenges for us to do for these wide coverages? Who go first?
I don't know. If you want to provide very wide area coverage with mmWave alone, that sounds a little bit odd setup to me. I mean, we already today in some buildings, etc., could be difficult to go outdoor to indoor and so on, even at lower frequencies, and those problems just get worse at mmWave. So standalone mmWave, yes, for certain applications like the factory halls or limited areas, so maybe a stadium or something like that, definitely, but not countrywide. Then I think you need to combine it with the lower frequencies.
Okay.
Yeah, I mean, I think the only possibility there, and we're talking now more about satellite or, some high altitude platform use, but then again, you have other issues such as still the building penetration issues and things like that. So yeah, you could get, of course, very wide coverage with, non-terrestrial network type arrangements, I'll call it, to use the 3GPP terminology. But the point is, yeah. But that basically gets you a platform up there. And then you actually, interestingly enough, have to be much more sensitive of rain losses and things like that when you have very high rainy storms and things like that. And there's been years studies done by the satellite communities looking at things such as that, in various regions of the world, and what's the outage probabilities and things like that. But
thanks, Tiedemann. Maybe next, Mr. Professor.
My impression is that if you would really like to have a wide coverage support only by millimeter wave, that would be very, very challenging, and especially because of this nature of the channel that we said, we can have blockages, we can have very different situations at different places in the cell, and so much different that cannot just be, that you cannot just rely on the adaptivity of the receiver or of the channel treatment. Yeah, so actually you have to treat. This is what I meant before with personalization. Maybe this was not really clear, that we need a very particular treatment of a user in a very particular situation in the cell. Yeah? And that is something that needs a kind of, let's say, what I meant with a kind of personalized file layer setup for this user. And like if he would be in a very special small cell, densification we know is something that can help, but without having such a, how to do this adaptively, maybe with file layer. This is something I could imagine, what I said already before, where machine learning could help. Yeah, and I don't know if this at the end is really the goal. Yeah, this is what the guys who really build up networks know better. But if I would ask, how can we help to do this from an algorithmic point of view? I would say it's very challenging, and we had more to do than the standard stuff. Yeah, just by the adaptation of the file layer, I think this would not be enough.
Yeah, I think coverage, definitely coverage is the most important challenge for millimeter wave, especially for outdoor continuous coverage network. Currently, for the operator, even though in the desert, the intersite distance is about 500 meters. So this intersite distance is very difficult for operators to build a network with continuous coverage. So maybe we should increase the coverage for the microsite, and besides this, maybe we must have more nodes, new nodes. Besides the microsites, the nodes must be very cheap, the cost. So if we add new nodes in the network, the cost for the operator will be higher, much higher than before. So it makes the operator very difficult to deploy a continuous millimeter wave network. For outdoor coverage, we think maybe we should moreover, besides this coverage, mobility is also another challenge for continuous coverage because of the very narrow beam for millimeter wave. So I think the increase the microsite coverage to add very cheap nodes for operators, and to solve the challenge of the mobility performance because of a narrow beam. I think it's a big challenges for the outdoor continuous.
Yeah. Let me just make a comment here. Don't want to necessarily make an advertisement for Qualcomm, but we have a line of chips that are millimeter wave infrastructure chips, which we call FSMs. But the point is, these actually allow very compact millimeter wave, I'll call them access points because they're more that size of an access point. And the nice thing with millimeter wave is you can build rather compact antennas with very high directionality. People have been using 128 and larger antenna elements, on these millimeter wave systems and things like that. And these things are very, very, can be very, very compact and put up there. So you really just need some power and potentially some backhaul capability, such as fiber there. Of course, the real challenge here that some of the operators are facing as they densify their networks are really worrying about the underlying prime power consumption, of their total network, which is quite a bit for operators in many cases. But I think vendors as well as 3GPP have been focusing a lot on trying to figure out how to deal with this in smart ways, where maybe you can dynamically shut down frequencies or something like that when the load is low, and then you realize that, hey, there's a user in here that's trying to send a real amount of data, and gee, I can offload my lower frequency network up to mmWave. You kick on the mmWave cell site, but all sorts of potentials here are possible, I think, with some real cleverness and innovation by the community.
And any panelists want to add something? They have a lot of questions in the Q&A in the wait list. So maybe we select some of them to discuss. One question is from Raj. Maybe this question is very easy to answer. Maybe Stephan can take this question. Are there any reports outside from the industry that allow full evaluation of mmWave performance?
I'm not sure I can answer that. I have probably a lot of reports, and the signal research usually go around and measure network quality and so on. So, but I don't have any particular report to highlight.
Maybe 3GPP is one of them.
Yeah, actually, there are other ones. There are a number of things out there. You just need to actually be careful looking at the methodologies of some of these reports that are not done by, I'll call it certain people who fully understand, all the details and the subtleties of how it is. In my presentation, I referenced, the report by OpenSignal, which could be potentially misleading if you didn't understand what they were actually doing and all of that in the way they did their report measurements and things like that. So.
Okay, thanks. The next question is from Wang Yi. His question is, there are many research on mmWave positioning for the large bandwidth. So standardization is ready in release 17. So is it the right time for the massive commercializations? If not, what are the main challenges to solve in the next years? Standard chipset or a market requirement?
I'm going to say it's the business issue. And it's also where the information is available on location. So for example, most people are getting their location information on their cell phones, such as, for Google Maps or something like that, but we actually have very good location, and many of these techniques really help with the location information that's sort of held by the network. But the question is, are the operators able to make a business out of this? Now they have, in many parts of the world, legal requirements, for example, for location information, such as for emergency calls and things like that. But those requirements are not to the accuracy that you could potentially get with mmWave. So the question really ends up being, what's the business incentives here, and how does the business all really work, here versus potentially the over-the-top players versus, I'll call it, the operators, and sometimes where the actual location information really is.
I think you should probably look for different type of use cases than the standard MBB, Google Maps type of positioning thing, non-consumer things, more kind of construction industry, factories and things like that. Because one of the first questions I usually got when I went out to talk about 5G a couple of years ago from people was, what about positioning? Can I accurately position my thing here? because people that were building houses in construction business, things like that, they wanted to know where to put the walls, basically. So
but
that's a little bit more specific use cases there than the consumer ones.
Yeah, I fully agree with Stephan. This is where you may have building contractors or special use cases willing to specifically pay for some of this information because it creates real value to them. You know what I'm trying to say? And so there you can look at some of these business cases potentially working.
Yeah. Any other comments on these questions? Positioning? If no, then we go the next one. Is adaptive. The question is Sidelink currently supported in 5G mmWave? And is it useful to support it? And for what type of applications? Sidelink mmWave.
If I recall correctly, Sidelink is just in FR1 at the moment in the lower bands, isn't it so?
Correct, yeah.
The answer to that question would be no, then that it's not supported right now in mmWave.
I think it's a very interesting question on supporting it in these higher bands. Yeah, but mostly, you know, the most usage of Sidelink so far has really been in the CV2X type of usage cases, which have been the specialized for the automotive industries, is where we're actually using Sidelink to some extent, you know, in actual real systems.
They have the question have what type of applications? Maybe you can add to this question. If not support, but for Sidelink mmWave, what kind of applications can use this? Maybe Yushun can.
For Sidelink, I think it's not the Sidelink problem is not only for mmWave. It's also a problem for sub-6 Yeah, the use case and business is not clear for the Sidelink technology. I think now. So like how to deploy the Sidelink in network. Yeah, it's very difficult. The business is not clear now. Yeah.
Yeah, but I'd just like to make a comment. I think there's opportunity for more Sidelink, but I think the point being taken is the business is a very key aspect of it. And as you know, 3GPP did some Sidelink work many years ago, and there was quite a bit of effort by some players to really try to figure out how to make that commercial for certain types of use cases, and that was not particularly fruitful because it wasn't adding the value over, I'll call it, more traditional techniques out there. As I said, the CV2X, where you do have certain cases and things like that, where it certainly does make sense. I think there are other cases where it really does make sense. Public safety has been certainly interested in it when they don't have connectivity through the network. And so I think there are cases where Sidelink makes sense, connectivity through the network. How the mmWave quite fits into that's not, I think, yet clear from a pure business perspective and a use case perspective.
Okay, the next question may be more exciting. I think Professor mentioned lots of times for the AI roles in mmWave, and this question is for AIs. This question is from Yan Sun. There should be an enhanced IR interface for tracking the challenges that mmWave is facing? Could AI play a role in it? Which particular challenges are most suitable for using AI to resolve it? Maybe Professor go first.
Yeah, I think definitely yes. I answered this already on the chat. As I said also in my introduction, is what comes with mmWave, which is a curse and a blessing both. Yeah, is the structure of the channel. Yeah, and if we can exploit this as much as possible, we are benefiting from it. Yeah? And that is the question is with which kind of methodology and which kind of technology do we exploit this? Because the problem is the more structure we have, we can more exploit of this structure, but the techniques become more and more sophisticated and more sensitive against errors and so on. And therefore, that's my point, that I guess machine learning can help here because it has a typically a inherent robust nature. Though it's not model-based, you are benefiting a lot from training examples. The question is where do you get the training samples from? This is what raises some skepticism. We can also discuss about this. But I guess, yes, for really completely exploiting as much as we can the structure of the millimeter wave, here AI may help. Or classical methods, but the classical methods are here might be more tentative, and that is something what I believe might help. What we did with some recent publication to show that it helps for estimation, that it helps also for example, having personalized code books for users, which is something for the moment a no-go. You can have a code book typically in a system, and that holds for all users, and it must be agreed on before by standardization how to personalize a code book. I personally believe with machine learning, this is doable, and that enters completely new directions. So I think AI, yes, might help here to some extent. What it cannot help is the problem of the coverage and so on. We cannot outrule the physics. But we can do as much as we can do. We can do with AI, I guess. I would say more, or not more, but maybe more doable and with more efficiency with AI. That is, but that is definitely a conjecture that must be shown.
Yeah, I think we're going to find, I believe one of the areas of interest, at least for 3GPP release 18, is really starting to do some study work on the usage of AI, from an air interface. And of course, this is beside the issues of implementation, which are up to individual companies. But the question is, in 3GPP, in our 5G advanced specs, and then also leading into 6G, where does it make sense to use some of these AI techniques versus traditional techniques? One needs to trade off performance advantages, plus of course, any complexity changes and things like that. And of course, today, at least in the cellular space, battery consumption, power consumption is a very important criteria. Also in this, so I'm sure it will be looked at and debated quite significantly over the next many years.
As I said, as coverage is the most important challenge for many people. I think AI, for coverage, the AI can only play a very limited role in coverage enhancement. But in other aspect for mobility performance, because beam management is very complex now for the beam management in 3GPP now. So I think AI can do something to increase the mobility performance, just like the beam steering or beam tracking with low overhead or latency, just like this. I think AI can do something.
Maybe I can just add one thing, because when we talk about the potentials of AI, maybe or any other system, I often have the impression that there is a misconception. AI or machine learning techniques won't bring gains which are completely new, which are not accessible anyway in a different. No, definitely not. It's just a tool, And the question is not, can I even do better and better and better? The question is, what's the effort I have to do in order to get the gains and the performance? And I guess the promises with AI is that you may get the same gains and performances, or a little bit less than what you can do with conventional model-based techniques, but with less effort, and more robust. Yeah, and because what we have seen is I'm working in this MIMO area for decades now already, and we have developed so many algorithms. Yeah, very, very subtle algorithms, and how many of them have ever been implemented in the networks? Yeah, you know it better than I know. Not so much. Yeah, and what's the reason for that? Is because they have a huge hunger for very precise channel state information, which you not have. Yeah, you don't have it. And if you now can offer a technique that can handle this lack of stable and very precise channel estimation in a better way than all this model-based stuff, then you can reach what has always been promised, but never have been achieved with the classical methods. Yeah, and that I think can be the role of AI, but nothing magic. Yeah, you just may get whatever have been promised, but now you really get it. Maybe with AI. That is my personal view.
Any other one to add comments on this? Okay, let's go to the next one. And next one is also the question I would want to ask is, we come back to the coverage. AI cannot solve the coverage issue, but other technology may. For example, the question is the race. Maybe they have another technology like IAB or repeater or smart repeaters. So we have so many technologies to improve the coverages. And then can you share your views on this this kind of technologies?
Yeah, I can try to start. I mean, reflective intelligence surfaces, that have been a popular research topic lately. And at least my personal view is that if I anyway is going to put up a surface that has some intelligence that I remotely control and then do something smart with, why not put up a base station or a repeater or an IAB node or something? So I don't really see what additional things the reflective intelligence surface can bring in that setting. Of course, if you have some passive reflector that does not need backhaul and power and so on, then it could play a role, but then it's basically just a piece of metal or something. But if you anyway need to pull a backhaul there, you need to put power supply there, you need to put some intelligence on that surface. I think why not put up an IAB node or a small base station or something? I could see maybe there could be some reason if there are some EIRP limits in the air that you're not allowed to put in more active transmitters or something like that. But then you're more into some regulatory peculiarities rather than technology.
Any other want to add comments on this one?
Yeah, I can say that RIS is, for me as an academic, a very interesting playground now. Yeah, and we of course want to see what we can do. Yeah, in an algorithmic way. That's interesting. Yeah, and it's currently a hot topic, as has been said. Having learned this lesson that this very sophisticated algorithm are very difficult to be implemented in real systems, I wonder how much complexity such schemes bring. Yeah, and how I remember that we had also this, which is now it became quite quiet. We had this relaying stuff, cooperative communication and relaying, big topic in the information theorists communities where I'm also in. Yeah, big topic. But how much of this has been implemented? And why? I mean, we ask why has it not so much been implemented? And then I wonder. So I think it makes a lot of sense, but we have really to clarify how to keep the complexity and the need for channel state information and stuff of this quite low. Yeah. Otherwise, I see that maybe it will go the same way as this relaying stuff goes. Yeah. Maybe this is a too pessimistic point of view of an academic. I like this topic because it's very interesting to talk with colleagues about how to do that stuff. Yeah. But if we think about implementation, yeah, we have to go some miles, I guess.
Yeah.
IIS is a very hot topic now. It can, in some scenario, it can provide some coverage for the blind area in mmWave area. As you know, but because of there is no PA, no PA in NIS, so the coverage is very limited now, and maybe 30 meters or so. It's very difficult for the operator to find the blind area and to find a location to install the IIS equipment because of very limited coverage. And the IIS and smart repeater can provide better coverage, much better coverage than IIS. So it's easier for the operator to build the network with the IAB or the smart repeater. So, but you know, the IIS is cheap. Maybe it's cheaper than the IAB and smart repeater. So eventually, I think it's a balance to balance the cost and the performance for the IAB smart repeater and IIS. To be honest, it's not clear now what's the best solution for the operator. I think the directions of the technology should be researched more to have the better performance and low cost to make the solution better. So we can help the operator to choose and the proper solution for them. Yeah.
Okay. Tiedemann, do you want to add some comments on race?
I'm okay right now, unless you had a. Well, I mean, go back. What was the question again?
Can the race help improve the coverage for mmWave?
Oh yeah, I mean, there are lots of things that I think we can do in mmWave to help improve coverage. I think we talked about small cells. Relays are good. I think some people have talked about repeaters. You know, all of these things, you know, are potentials to help improve the coverage on these small cells. I mean, you know, of mmWave. And what we're seeing also is, of course, many of the operators, as they're deploying mmWave, are actually densifying their networks. And part of this is, you know, just overall the issues of going to higher frequencies, higher data rates, even for, you know, where we have 3.5 gigahertz band. Yes, in 5G we have much more, I'll call it antenna usages and things like that. But the point is we're going up in data rates, and particularly on the uplink. This is always a challenge to get the uplink data rates, you know, up there with good coverage.
Thanks. Maybe we can go this. Have following questions on this race coverages. So we have for the coverages we have many tools. And not only we have a relay, we have IB, we have a repeater. Now in release 18, maybe potentially we have a smart repeater. Then maybe later on, maybe we have a race. So we have so many tools, but these tools is for the different scenario or is for the same scenarios. So can you comment on this one? Or if they have different scenarios, then what kind of different scenarios for these tools?
I guess I didn't get the question, to be honest. Can you rephrase this?
So now we have so many tools for enhance the coverage. We have a relay in LTE. We have in 5G. We have IB node. Now we have a repeater, RF repeater. So also we also maybe introduce a smart repeater with beamforming. So we also have a race. So now we have 5 tools to enhance the coverage. So my question is, these 5 tools is for the same use cases or these 5 tools is for different use cases. If this is for different use cases, then what kind of use cases you are thinking about for this kind of encourages this network element?
I think you can add one more tool to that list, and that is to put up a base station. With
a base station, yes, that's definitely
solution to densify the network that way. And
yeah.
where do you want to do that? Of course, if you have fiber and have a good place to put up the base station, I don't see why you shouldn't do it. Of course, IAB know that's in essence a wirelessly backhauled small base station in some sense. And depending on what spectrum you have available for your backhaul link, it may or may not make sense. I think one of the reasons why relays in LTE didn't take off was that you actually have to waste your precious access link spectrum on the backhaul. And that you didn't want to do. That may be different in 5G now that you can run mmWave on the backhaul where you have plenty of spectrum. So that could potentially change the situation.
Yeah, exactly. And particularly even some of the higher frequencies on the backhaul there. But I think the key thing is there are a bunch of techniques that are out there. I think it's going to be what gets deployed is going to be the offerings that vendors of all types put out there, and then the cost effectiveness for solving the particular issues of the operators, at the time, and their needs.
Any other comments on this? If no, maybe we can go to the next question in the QA list. AI already asked. Okay, for this one, Song Yanxue, the question is, in addition to the coverage, does there any power consumption issues for mmWave? As we know, mmWave have very large bandwidth. So there are any power consumption issues? If yes, any potential solutions to handle these issues?
Yeah, I mean, I think there are a couple of things that are important to understand here. We have a lot of bandwidth potentially at mmWave. The component carriers are typically 100 in most of what's deployed right now, megahertz wide. So that's a lot of bandwidth. But I think the key thing to also understand is if you do the right management, the time that the actual user device, UE, is receiving or transmitting can actually be much less, because you can send things in very, very short bursts, certainly, or receive things in very short bursts there, and then do power savings in the rest of things from there. But you are right. I mean, if you're sampling 100 megahertz of bandwidth and having to process that takes more power. And as implementations are getting better in handling these various things, then we'll be getting much better overall in the power consumptions of devices at mmWave.
I think this, I mean, I have the same issue on the infrastructure side on all frequency bands, because the power bill is a quite big expense for the operator. So reducing power consumption is of interest. And I think we start to see those things happen, especially with the 5G standard, where we don't have any common pilots and CRSs being on all the time. You can actually build something where power consumption scales with the capacity you need, the amount of data you transfer. I think that's a lot of implementation things. And the infrastructure side starts to do what the device side has done in the past, to sleep more, shut down circuits that they don't need at the moment, and things like that. So that can help a lot.
Now, the power consumption is also a big problem for mmWave deployment, not only for the base station, but also for the handset. So I think maybe also the beam management is also a big challenge. To increasing the coverage, we know the millimeter wave is very narrow beam. So, the network use a lot of resources to do the beam scanning. So, how to decrease the resources used by the beam scanning and beam management, and maybe the a very important direction for us to research. Yeah.
Yeah, I'm not doubting that you can always likely enhance many of these techniques, but as I said, right now things are out there working pretty well on millimeter wave, and we've solved the key challenges of being able to do, beam management, on the handsets, and I'll let Stephan talk about it from the infrastructure side, because that's his bailiwick per se, but and of course anyone from any of the other vendors on that. But we've been able to solve many of these things, and we're really solve these things and really get systems out there. I mean, the number of phones and devices that are out there now that have millimeter wave in them that are 5G is quite large right now. And we certainly know, just to give you an example, all the operators in, there's a lot of deployment in the United States, a lot of deployment now in Japan, where all 4 operators actually have some millimeter wave coverage at some level in Japan. What sort of slowed it down a little bit in the rest of the world is really the availability of sort of, I'll call it the spectrum around 3.5 gigahertz, or some. And by the way, I know China's a little bit different, because China mobile was at 2.5 gigahertz there. But the point being, having these lower frequency spectrums, which are what the operators have really focused on in many parts of the world in their deployment so far of 5G. Where that's been available, just because that's sort of like the deployments that they've done in the past, to be very blunt about it. It's, millimeter wave requires a lot of really understanding, and education in the operators from a deployment perspective, and to understand it, even though you can actually do very, very well in doing it, but it's a different, it performs differently. And so you have to start thinking about it and get that expertise on how to actually use it appropriately, as we've been talking about earlier in this panel.
Okay. Maybe we can move to the next question in the Q&A. One question maybe is related to MIMO from Jinghuan Ping. His question is, for mmWave, we have done our base station deployment. So could the cell-free technologies more promising for mmWave?
Depend what you mean with cell-free, of course, because that's one of these maybe I could call buzzwords that different people put different meanings in. I think, fundamentally, the coverage is physics, boils down to physics and wave propagation and things like that. I do think, though, that you can have, if you have some, call it cell-free or distributed MIMO or multi-TRP or whatever, where you can transmit to the device from multiple antennas that are geographically a little bit separated. That can, of course, help, especially when it comes to reliability. If you block one path, you at least have one other path still functioning and things like that. But just calling something cell-free, I don't think that will solve the coverage issue as such, unless one be more specific what cell-free is in that context.
I think there are opportunities, but it's going to take a big thing there to use and really deploy techniques such as relays. There's work going on in 3GPP, looking at other sort of things. I'll call them roving cells, cells on wheels that are really dynamic, if you know what I'm trying to say, on these things that might be at buses and things like that. So I think there's a lot of opportunity here to at some point, use devices out there to, improve coverage, of networks. But I think it's going to take a few years for all this to practically work out, and the business cases to be really pulled together on these things. But there's a tremendous opportunity, and I think to use some of these techniques to some benefit.
Mm-hmm.
I would say the main idea of cell-free technologies is or has been sort of invented for getting rid of these cell edge effects. So because by these and this is a question if this is a special problem in mmWave comm, it's in all systems, maybe an issue in it. So I would say cell-free technology does not necessarily already help, but there has been mentioned a couple of times now already that densification is an important thing. And I think if we would talk about densification, then the question is how the network is organized. And then I would say densification plus cell-free, that is an interesting, attractive solution, I would say. So without having done any studies about this yet, I would say that would be interesting. Yeah. But just cell-free is not yet the point. Yeah, though this is my 2 cents.
Yeah, for cell-free, I think before we use cell-free technology network, we should have the continuous networking first. So the big challenge is that with operator, it's very difficult for operator to build a continuous coverage network. It's a big challenge. So that cell-free is not a priority for mmWave. Yeah.
Okay. So we can move to the next question. The next 2 questions is related to the hybrid beamforming. I think this feature is hybrid beamforming is quite dedicated for the mmWave. So the first question is from Yang Sun. The question is, will the hybrid beamforming always be the only structures for mmWave? And the following another question is the optimizations of hybrid beamforming in mmWave face many challenges, such as self-signal deteriorations, hardware constraints, and design complexities. Is AI promising technologies to optimize hybrid beamforming? Maybe we can discuss these 2 questions together.
Maybe I start with I don't see why. So maybe we talk about beamforming. Hybrid beamforming, I don't see the point why AI, for example, should be more help for hybrid beamforming than for beamforming. So I don't think all the issues that come with the hybrid part. I'm not see so much that the AI helps here. But generally, the question is how to do the pre-coding stuff and the beamforming and how to do this. And so when I'm advocating AI, I'm not thinking so much about replacing standard beamforming techniques by AI. I have seen that there have been in some papers many of such attempts to say do not run this complicated pre-coding or not, so whatever pre-coding algorithm, and replace them by AI methods that may find immediately the right beam or stuff like this. I do not really believe so much in this because I think that the standard methods here are quite robust and good. So as I already said before, I think the AI more helps to get the right way of how to deal with the channel state information, how to get it, and how to maybe have a substitute of this, and that is something I think is more. So just the issues or the challenges that come with the hybrid aspect, I do not think so much that AI is the solution. It is because this is something in the technology. I don't know if this is a question you have been expecting, but I wouldn't say so. That. And is there anything else? I had the impression over the last years, I had some projects also with industry a couple of years ago, how about the potentials of hybrid and how can we do better beamforming algorithms, hybrid beamforming algorithms, stuff like this. And I had the impression there has been some development in the companies. Yeah, they have already somehow 256 massive MIMO antenna stuff with hybrid beamforming. But my impression always was that there is a principal functionality, but not with the full degrees of freedom that we algorithm designers wish to have. Yeah? That seems still to be a lack. And then I have seen many developers that told me maybe we remain with full digital networks, with arrays. So I'm not really aware of where the discussion at the moment is. Yeah, do we really go for hybrid beamforming or partial? This is another buzzword is partial arrays, yeah, partially connected arrays and stuff like this. I had somehow the impression that there was a return back to fully digital. Yeah, I don't know where the situation at the moment is, and yeah. Another question is also the slow bit stuff. Yeah. There had been low bit beamforming as an alternative, but fully digital, but low bit. Yeah, so you have cheaper AD converters and stuff like this. I think they are different. I actually am not really aware about the answer. Yeah, if we have already the solution, even not from the companies, but maybe you know it better. If there is already a direction which is obviously the solution.
I think there is a little bit of direction going towards more and more digital beamforming. I mean, analog beamforming is motivated by implementation constraints and so on. But as technology advances and as you come out with more and more mature products, you will see more and more processing done in the digital domain. And I think that is good to keep in mind because quite often in 3D PP standardization and so on discussions, they were talking about beam sweeping and these type of things that were very analog in their mindset, so to say. So it's important to ensure that whatever standard you cook up, that also can handle the evolution of the implementation technologies when you go to more digital implementations.
I mean, you mentioned that with the beam sweeping, that has been already mentioned a couple of times, which is quite an effort. And this is also something which I meant when I was talking about this personalization stuff. Imagine a situation in a cell where each user at a certain position has a kind of footprint, what the best beam sweep combination might be. Yeah. So that is something that you could lay down in a table, which is difficult, yeah, and which is cumbersome somehow. But could this be something that you learn? Yeah, very personalized for user and for places and locations in a network. Yeah, how to do this is not trivial. Yeah. But I think to do it model-based is not a way. Yeah, to lay it down in a table, I would also not go for. Yeah, but maybe you can learn this in some sense. And sometimes a neural network is a kind of implicit table. Yeah, you learn a situation. Yeah, and that is something that can be also easily adapted. Then, and this is something. When you were wondering what I meant with this personalization stuff, yeah, this is something like this. Yeah, I haven't seen so much in this direction, but I guess to have this very costly sweeping stuff and so on, why can we reduce this effort a little bit by just having background information? Because you do this again and again and again for each user, and a new user enters the area and you do it again. Yeah, and you have not, you might, and many techniques have not learned from has been done before. So let's keep the history. So most today is in a different way. My impression is that most of the data in a network on the file layer level, most of the data is thrown away after it has been very costly acquired, it's used, and then it's thrown away. And I think this is something that we can change with AI, but it's not trivial.
But I think when we talk about AI, I mean, there is quite a bit of discussion on AI in preparation for release 18 now, and this CQR reporting, the code books for CSI state reporting, that is one of the areas where a lot of companies are active and bring up as one good starting point to apply AI and see what we can do there, come up with more customized code books.
Definitely. Yeah. By the way, we have a work on this. You may be interested in it. I can share it with you.
Yeah, good. Maybe we can share a plan. Any other comments to this hybrid beamforming? I think we are almost run out of time. So maybe I have last questions regarding to this industry application, like the Tiedemann mentioned the smart cities, smart manufacturing, this kind of use cases. So for this this kind of use cases, what the special technical challenges for us, and what's the research directions for this use cases?
Yeah, I think actually there are certainly some technical challenge. I think the biggest challenge is what you were starting with is actually educational. And I think there's a tremendous potential, and certainly as the research community turns a lot to 6G, but to really also learn how and get confidence on using many of these 5G techniques in many of these, I'll call it adjacent industries. We call them in the telecom world verticals. You know, and say in the automotive area, we're doing relatively well. You know, in certain industrial ones, yes, but there's a huge number of places where some of these technologies, whether they're sub-6 or millimeter wave, can really be used, and these provide a lot of opportunity. I think particularly in the academic area, there's real potential where you have a lot of easy cross-fertilization between, say, university departments and things like that, to really try to help, you know, show how these things can be used in many new use cases. I'll be quiet and shut up now.
Yeah, I think for the also for coverage. So maybe in the future we can design some new R interface for mmWave separately. For example, we can research some new waveform to change multiple CCS to single CC, just like in my presentation. So we can get low JPR and better coverage. We also know for beam management is also a big change. It's a very narrow beam for mmWave, makes the beam management very complex. So maybe we should design some advanced beam management algorithms with super narrow base station and the UE beam, such as quick beam steering or some tracking with low overhead or latency. Second, also for coverage, just like Zhengqi said, AB, relay, IIS, smart repeater, yeah, whatever. A lot of candidate solution for to solve this problem. But how to optimize and choose the technologies to balance the cost and the performance is a very important research work we should do next. Thirdly, just like for the uplink service, I think maybe we can design some novel RF architecture and optimal system capability algorithm, enable flexible FDM or SDM multiplexing. Another challenge is also the different TDD configuration to increase the uplink capacity. So as you know, the strong cross-link inference is also a very big challenge. Moreover, for the sensing capabilities, maybe we can make full use of the super narrow beam and broadband features for mmWave to increase the accuracy for positioning or sensing. Yeah, but the sensing and capability and communication should be combined together in the same hardware, same frequency, and same air interface. At the same time, the sensing capability can't affect the communication performance a lot in network. Yeah, moreover, the sensing can help maybe the sensing capability can help the communication performance to help the communication to get better performance. Yeah, I think it's the most important directions for the research next.
I think one thing we've seen in the past couple of years, I mean, we have a 5G specification ready, and you can simulate a certain performance, and you get a certain performance out of the real networks. And what we see is that the with the improvements in implementation that people learn how to do algorithms, both on the US side and on the network side, we have seen quite big steps in improved performance. So it may not be the first thing we should do to run off and change the waveform or put in more stuff in the standard. It's also a lot about products maturing and coming to this. A little bit what Ed was touching upon as well, that building a mmWave network is different from building a 2 gigahertz network, for example. And it takes time for operators and manufacturers and vendors of all kinds to get into this as well. So I think quite a bit will happen on that, the implementation side.
Any other answers, questions? Oh, if no, thanks to all distinguished panelists to share your so many great ideas in these panels. It's very useful for us. So we have so many wish lists for mmWave. So I have all of these wish lists can fulfill in the futures. So before we close this session, maybe we can take a group photos virtually.
You mean in person together?
Can we maybe just to take a snapshot?
Yep, I can do it.
Yeah. And while waiting, thanks also for running a panel where we actually had a lot of discussion. I like that. Well done.
Thank you. Yes. So for me, it was a pleasure to be accepted here as an academic in this more industrial related panel. I learned a lot of things, and you saw I could not keep with you in all these elements, but I hopefully could share some thoughts with you. It was a pleasure for me, really. Thank you very much.
Yes, and also on behalf of 6G Flagship and the PMRC organizing committee, I would like to thank Zenfei and all of you for holding this panel. It's very interesting discussions. I think I've been in many of the panels, and this is one of the ones with the most lively discussions. I mean, even now we are a bit over time, but still there are a lot of questions that have not been answered.
Yeah. Thank you. Thank you for attending this panel. Thank you.
Thank you.
Okay.
Thank you.
Bye-bye.
Bye.
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 Have a nice evening.
Good night. Good day.